All right, so PA5 is all graded and recorded, and mostly that seemed to go pretty well. Most people use the test code to test their own solution, and we're able to get a good solution. If you were getting the wrong numbers from your egg function, the cases that I was able to sort of dig into the code and find what was going on, it was usually just not using exactly the right formula that we had on the assignment. So, you know, just having an off by one somewhere in the expression, or not looping correctly, not iterating through all of the possible floors. And so let me just pull up the assignment. And look at this algorithm once more. So your function that you're writing is egg, okay, floors comma eggs. Some people used, you know, A comma B, and then partway through the code switch which one was floors and which one was eggs, right? So it's usually helpful to actually use like more meaningful names like floors and eggs. So there's base cases, right? No floors, or only one floor, it takes one trial. Only one egg, it takes floor, number of trials. But this piece in here, right? So you need to make two recursive calls to the egg function. One is here, one is there. And then you need to take the largest of those two, right? So you can write a max function, or you can just, you know, use an if statement. There were some max functions I saw like this. Whoa. Come on, you can do it, you can do it. Oh man. Hey. All right. So I saw a number of max functions like this. If A is bigger than B, return A. If B is bigger than A, return B. What's the problem with that function? If they're equal, you're not returning anything, right? Well, you are returning something, but you're not controlling what it is. And you know, sometimes you'll luck out and it'll be A or B because they got pushed down the stack and your return is coming back through the stack maybe, but sometimes you just get weird stuff. And so, you know, you could do if B is greater than or equal to A, return B, or you could just make this return B, right, which is kind of like, or you could say else return B, right, or, you know, there's the one-line version. So the ternary operator says if A is bigger than B, then this expression is equal to the thing before the colon, so you return A, otherwise you return B. So Java, if you do something like this, right, it'll warn you there may not be a return value, right, but C doesn't care. It's like, sure, no problem. So you have to catch those things yourself. So yeah, find the largest of these two calls to egg, take the largest, add one, and then find the minimum of that expression across all values of f, from 1 to floors. And in some cases, people went from 0 to floors, or 0 to floors minus 1, or 2 to floors, right? And those are slightly different versions of this. So if you weren't getting the right number, right, it was probably just something like that. But, you know, ask me about it. Tomorrow's open lab, so you can come by and work on that tomorrow if you want. Yeah.
Is it a good idea for us to remember this specific algorithm?
If I asked you about egg dropping, I would give you this algorithm,
Okay.
or rod cutting, or knapsack. if you were seg faulting, assuming that you set up your array correctly, and you weren't mixing up floors and eggs some way through, if you were seg faulting, it was probably still something in the main definition of the egg function, something where you had an index going negative, right? Or you weren't catching a negative number of floors or a negative number of eggs. This should never give you a negative number of eggs. Eggs goes down by at most 1, and when eggs is equal to 1, you have a base case. But if somehow your number of eggs got negative and you don't check for that, you're going to make a recursive call to eggs with egg with eggs being negative, and when you look in your save array, it's going to seg fault probably. So seg faults can pop up just because of an error in how you're recursing. So those are all just details, right? What I wanted to make sure that everybody hears is this business of adding the dynamic programming. Okay, and this is a general prescription. So you've got a function called slow function that takes some arguments, and let's just say it returns an integer. And you do some slow and long calculations, and you finally end up with, answer equals something, and you return answer. Okay, this is your recursive function that's not using dynamic programming. Okay, and it looks like this. You do a bunch of stuff. You make recursive calls. You do whatever you have to do up here that's taking like a really long time, and eventually you end up with the final answer, the value of your function, and you return it. Okay, if you want to add dynamic programming to speed this up, you don't have to change any of this stuff. Okay, you don't want to change this, for example, to where your egg function is looking at your save array, right? You can do that if you do it just right, but it's not always going to work. It's going to work in some problems where you're guaranteed certain properties of how your save function is being used. But in general, don't monkey with all of this stuff inside your code. Okay, all you want to do is add one thing in the very beginning, one thing right before the return, and one thing outside of your function. Okay, and this is the only global you should need in this whole thing. So declare some kind of space for storing return values. Okay. And initialize it to some value that lets you know whether or not you've put a value in there. Okay, so some people initialize it to floors plus 1 because you're never going to need more than floors trials. Some people initialize it to 2 billion. You can initialize it to -1, 0 works in this case, and so on. But set up some kind of memory. Okay, and then in the beginning of your function, look for that function value. Right? Depending on what your arguments are, how many arguments, whether this is a one-dimensional array, a two-dimensional array, a linked list, a hash, a tree, whatever, right? This is some place where we can store return values for different arguments. In the very beginning of your function, just check that memory location, see if it's been set. If it has, just return your value from that memory location. If not, do everything exactly the same way you were doing it in your function before, but then at the very end, before you return, just save it. Right? So you're not messing with any of the code inside your function. You're adding one thing in the beginning, one thing right before the return. And that's the cleanest way to add this dynamic programming in, right? It's really just a memory cache. Does that make sense? Cool. All right, well, let's just take a look at what I posted. I don't think there's any surprises here. So I put some dates on here so it'll show up on Canvas. It's marked as March 16th, but if you come to the Wednesday one, it's Wednesday. But otherwise it doesn't show up under upcoming. All right, possible topics for final exam. So any questions before we just go through this? About anything? Yeah.
Where did you get the idea for PA5?
Oh, egg drop is a classic dynamic programming type question. You can Google and look for dynamic programming problems, and you're guaranteed to see knapsack, rod cutting, egg drop, greatest subsequence sum, longest common subsequence. There's a whole bunch of them.
So after we finished PA5, we actually looked it up online.
Mhm.
Apparently that's what Microsoft was using for interviews.
Oh, really?
Last year.
Oh, interesting. Okay,
So
that's
thought
cool.
that was
I wonder what they were using the year before. It'd be interesting to see if there's a trend.
Is it like Mac drop or something?
Yeah, right?
It's whatever you used for PA5.
Probably, they're probably just watching my videos. That's awesome.
You had your Windows terminal come up or something?
Yeah, yeah.
Yeah, I mean, I know someone was doing Gate code, and I was taking a look at some of the stuff they were doing, and a lot of it was just the ODPs that was doing.
Oh, really?
On Gate code, yeah.
Okay,
So that's pretty cool.
cool.
He's preparing us for the workplace.
Yay. Go figure.
Interview with this.
Yeah.
Well, if you can get the interview, you got the job, then you can stack over whatever else.
That's right.
They don't never read it.
Yeah. I think I saw some Discord chatter on that. Cool. Yeah, I mean, these are classic problems, but they sort of, you know, they hit cores that can come out in a lot of different forms. But if you can figure out how to deal with the egg drop, right, and all these other problems are pretty similar, just different specifics. These Google challenges that I was doing were ambitious, more ambitious than I would do for, like, you know, a programming assignment for a class, just because they had lots of different parts and pieces. But the parts and pieces were really, you know, they're things that you do in these classes or that you'll do in other classes. And so interview questions in general are sometimes they're tricks, you know, but a lot of times it's just like, yeah, how much core knowledge do you have, but more importantly, can you put those core pieces together and come up with bigger solutions? And I think that's one of the more valuable things that employers are looking for.
I think the other interesting thing was that almost nobody knew how to do it.
Oh, really?
Nobody, it was most people couldn't even start,
Really?
so.
If you don't know, you know, how to come up with this relationship, right, you're kind of out of luck.
Yeah.
And I don't know if I would have come up with that. I mean, I certainly didn't come up with it when I first looked at this problem. I just found it. But, you know, if you've looked at that and rod cutting and knapsack and longest common subsequence, and you start to think in that modality, yeah, you can probably come up with some of this stuff. But on the other hand, if it was like 2 years earlier, you know. All right, well, let me start from the bottom, because the bottom is the more recent stuff. So things you should be prepared to do. So, you know, there's some programming questions. So there's actually 3 programming questions, and then there's 7 non-programming questions. But the 3 programming questions are like 45 points, so it's about half the points. But for those, you know, you'll be writing code, either complete functions or snippets of code, things like that. to work with structures, manipulate them, definitely deal with pointers. So basically stuff we've been doing, mainly we've been working with lists and trees. We worked a little with hashes, but hashes were really just a wrapper around linked lists. So lists and trees get you most of it. So all the stuff that goes with that, malloc free, declaring things, setting up structures, things like that. Analyzing code, so I may give you code snippets and ask you to do some things to them, make some changes to them, or answer some questions about them. Definitely will be recursive code on there, right? Everything we've done in trees is recursive. So think about the ideas behind, what is left node, right traversal? Why do we write it like this, right? And to some degree, how does that work? So list trees, tries, hashes, stacks, queues, other data structures, all the things we've talked about. GDB, right? Hopefully people have made some peace with GDB and are using GDB to some degree. So know how to use the basic commands, how to compile with a -G switch, how to use GDB program name to start, running GDB, the start command, the set arg command to set an argument, breakpoints, watch points, printing values of variables, continue, step, next. That's pretty much enough to get you going. So try to be comfortable with those. Val grind, right? The idea when we malloc, we want a free, and val grind will let you know if you've got memory leaks, but also if you've got uninitialized memory locations. Make files, make sure you understand how to use a make file. Doesn't have to be fancy, but at least, this idea of file.o depends on file.c and maybe, file something.h. And to make a .o file, we use the C switch. Okay, don't compile your .h files. It'll give you weird messages when you make. The .h, if it's included in here, presumably, then it gets picked up when you compile. So use the -C switch to make a .o, and for your executable, just use a -O switch. Right, and that's fancy enough. Maybe a make clean. So make files, other tools, those are really the main tools, GDB, make, and valgrind. All right, so let me go through the topics. So heaps, max heaps and min heaps, okay, they're identical except for what the heap property says. For a max heap, root node should be greater than all of its children. For a min heap, root node should be less than all of its children. But as far as do you up heap, do you down heap, that's independent of whether it's a max heap or, right? So when you insert, you add to the last location on the bottom level, and then you up heap. To delete, you remove the root, take that last entry, put it up to the root, and down heap. Okay. We talked about heapifying, from taking a set of numbers and turning it into a heap efficiently, and we talked about implementing with an array by using that index arithmetic. 2 times a parent, and 2 times a parent plus 1 gives you a child, and so on. So that's what I want you to know about heaps. Sorts, I would like you to know bubble sort, insertion, and selection sort. Those are order n squared. Okay, they're the inefficient ones. Merge sort, which is recursive, splits your list in half, sorts each half, and then merges them together. That's an n log n. Heap sort, which is just throwing things onto a heap and then pulling them off in order, which is n log n. And quick sort, which is usually n log n. That's the one we did on the boards. That's a good one to know how to do for the exam. Hint. Where you have a pivot, which is the last entry, and you move your arrows and swap when they're out of order, and so on. We talked about radix sort, which was just going through digit by digit. All right, dynamic programming. That's this stuff, right? So if you have a function, know how to speed it up by caching results. That's the essence of dynamic programming. And it's usually used in problems that have this repeated substructure. So you can solve your problem by taking solutions to simpler problems and putting them together. That's what's happening in knapsack, egg dropping, rod cutting, and so on. Tries are that really wide node structure where you have, for example, 26 children, one for each letter of the alphabet, and you point to another node and you keep following links from letter to letter until you get to the end of your string, and then you set the end of string tag in a node to say there's a word that ends here. So we work through those on paper, right? Go back and review that, make sure you know how to do looking at a try and figuring out what's in there, or adding things to a try by manipulating the pointers.
So my recollection is, due to the way a try is structured, there's not really a way to just say, like, show me an element in this try, right? As long as,
You mean like traversing it?
think so?
Like showing all the elements?
Yeah, like,
That's actually pretty straightforward to do. And it's really fun to write. Right, we got other stuff going off somewhere.
oh, because you split off to a different.
Yeah, it's a very recursive function, right? Basically, so you could print out the letter A followed by everything that you get by following the A link, right? So let's say we're up to C, right? We're going to print out a C followed by each word that we get by following, whatever is non-null in here. You got to do a bit of work, maybe use an evil global or pass things around or something, but you got to let this thing know that whatever it's going to print from this point down should be prefixed by a C, or whatever it will print from this node down should be prefixed by a C and an A, right? But it's potentially 26 recursive calls, and when you get to a place where the end of string is set to a 1, that's the end of your word, so you throw out a new line or something. So you need some way to, so if you're going to do this recursively, you're going to say traverse, the try that's rooted at this node, but you have to tell that traversal that every time it does that, it should print out a C and an A in the beginning.
Could you just pass a prefix string?
I think you can pass it as a prefix string. Yeah, you just have to pick it up when you're jumping down. Yeah, just append your current letter. Yeah, that should work. So it's like 26 recursive calls, and you don't actually call these nodes, A, B, C, D, E. You make an array of pointers, and you iterate through there, and if it's not null, you call recursively, and you check for end of string. So I won't ask you to do that, but it's fun to do.
Thank you.
Yeah. All right, AVL trees. So these are the balanced versions of trees. So what do you want to know how to do here? Definitely understand what the balance factor is. Okay, height of the left subtree minus the height of the right subtree. You don't use balance factor to calculate balance factor. You just use height. So if you're writing in the balance factors and you make a change and you want to know the new balance factor, it's based on the height, not on the balance factors. Okay, and then if all the balance factors are 0, 1, or -1, your tree's balanced. And if there's a 2 somewhere, all right, starting from the node that you just inserted, work your way up. If there's a balance factor of 2 or -2, your tree is unbalanced. And you correct that by doing 1 or 2 rotations. Left, right, right, left, right, right, or left, left. And we did this on the board. We talked about it for a couple of days. So make sure you know how to do that, how to do the analysis, how to figure out what kind of imbalance you have and what the rotations are to correct it. Okay. Put those rotation formulas on your note sheet or something, unless you memorize them. Yeah.
So when it comes to implementing other data structures like queues and stacks, stuff that we didn't really work with, how important is it knowing that going to be on for the final?
So I would think about it ahead of time and have some ideas. If you had to implement a queue with a linked list, what would that look like? Okay, it's a good way to think about queues differently. If you wanted to implement a stack with a linked list, what would that look like? If I ask you coding questions related to stacks or queues with arrays, I'll probably give you the code. So I'd say, here's some code for implementing a stack, here's some questions about it to answer, that kind of thing. But yeah, I would just think about them, just review them a little bit, just as a way to make sure you understand what a queue is, what a stack is, and how they're different from each other. All right, binary trees. So this was a big part of the course. So binary search trees, right? The fundamental property, things on the left are smaller than the root, things on the right are bigger. Depth of a node, height of a tree. Depth is the number of links from the root. Height of a tree is the depth of the deepest node. If there's only a root, the height of the tree is 0. If the tree is empty, the height's -1, because there are no nodes. Traversal, mainly we've talked about depth first traversal, so left node left right node. Okay. We touched on breadth first traversal by using a queue, but the idea is you basically just move across each level. Recursive algorithms for searching a tree, inserting into a tree, and deleting a tree. Okay. And make sure you understand how to do those things. Right, and deleting, the algorithm we used was take the largest node from the left subtree, move that up to the root. The only exception, if there's no left subtree, then you're deleting the root, just move the root down. All right, and then hashes, that was PA3. Basically, I had an explanation for a hash the other day. I don't remember what it was. Well, it's like a dictionary, right? If you have a word and you want to find the word in the dictionary, well, your dictionary is huge. How are you going to find the word eggplant in there? Well, we use a simple hash function, which is take the first letter of the word. And based on the fact that the first letter of eggplant is an E, we go to the section that's labeled E, and we only have to look in there, right? And then inside there, we just search through in order because it's alphabetized. Okay, it's a really simple example of a hash. So a hash in general is a function that takes something we're looking for, a key, turns it into a number typically, and says, hey, look at this location in your array. That's where your thing should be. So with chaining, which is what we used in PA3, at that location in the array, we find the start of a linked list. And we just search that whole linked list for the word we're looking for. If we're not chaining, we have this idea of probing. We can store something at a location in the list, but if that location is already in use, we rehash and we try to get a different location. And we keep doing this. Okay, we mainly know about chaining because that's what we did for the assignment. All right, so queues and stacks. Stacks are last in, first out. Queues are first in, first out. And then everything else, right, we're well into the first half of the course already, and stuff that was discussed for the midterm. So recursion, recursive algorithms and programming, abstract data types, right, the idea of separating how the user deals with a data type versus how it's actually implemented, right? So the user view is looking at it as an abstract data type. Makefiles, GDB, malloc we talked about, pass by value versus reference, there's no specific things there. Asterisk, ampersand, dot, arrow, we've coded these a few times, right? Linked lists, we know about linked lists and how to declare a structure. Obviously how to make a main program and argc, argv, all of that stuff, don't forget all of that. Hint? No, just in general for life, you never know when it'll come in handy. That's pretty much it. I think everybody's in really good shape. I know you've worked really hard this quarter. I don't expect the final to be a big deal for anyone, so read through it. Make sure you're only doing what it asks. Right, and ask me if you're not sure, and it shouldn't be a big issue, and we'll go on to Java in a few weeks. Yeah, which you will like a lot more than C in general. which is why we don't do Java first, because you'd never do C otherwise. All right, so tomorrow's open lab. I'll be here both class periods. If you want to come in and work on code or talk about anything related to this, that's fine. Otherwise, I will see you for the final either Monday at 10 or Wednesday at 11.